Hello everybody, and welcome to the beginning of page 51 here. So in this page, we're going to start talking about the meaning of these matrices that we've been calculating. So we've done a lot of calculations where we take a linear transformation, excuse me, and we try to write down the matrix of that linear transformation. But you're probably asking yourself as you're doing these calculations, why are we doing this? What's the point of finding the matrix of a linear transformation? Well, we're going to finally unpack that and discover why this matrix is important and what it's really telling us. All right, so let's start by reading through this key fact together. So let V and W be finite dimensional vector spaces, T from V to W be a linear transformation, and beta and gamma are going to be bases for our domain and our codomain. So same situation that we've been looking at. Okay, next thing we're going to do is to take a vector in our domain, U and V, and this next sentence is going to be our explanation of what the matrix of the transformation tells us. Okay, here goes. Then left multiplication by the matrix T beta to gamma transforms beta coordinates of U into gamma coordinates of T of U. Okay, so what this is saying is that the transformation itself takes an input U and spits out an output T of U. What the matrix does is it takes us from the beta coordinates of our input to the gamma coordinates of our output. That's in a nutshell what this matrix is telling us. Okay, now I'd like to do an example where we really explore what that statement is saying, just so we can visualize it a little bit better. Okay, so in example 6, we're going to be referring back to example 4, where we talked about this function, T of P of x equals P of x plus 2P prime of x, and where we were talking about these two bases. Beta is the vectors 1 and x, and then gamma is the vectors 1 and 1 plus x. Okay, and they'd like us to use the matrices that we calculated in example 4 to complete the following. Okay, starting with A. All right, so in A, they're starting us off by referring back to a matrix that we already calculated, okay, in example 4. So I'm going to start by writing that matrix down. And I'm literally flipping back a couple of pages and just writing down the matrix that we calculated. A few pages ago, we calculated this matrix to be 1, 1, 0, 1. You can page back and check me on that. Okay, and what they'd like us to calculate is just to take that matrix, 1, 1, 0, 1, and to multiply it by this vector, 1, 2. Okay, so that's a calculation that we can do simply enough. It's just asking us to do matrix multiplication. And if you do that, you can check me, we're going to get 3, 2. Okay, now, what does this calculation mean? Well, here we're going to refer up to our key fact. And notice that what this matrix is supposed to do is to take us from beta coordinates to gamma coordinates. So we're going to interpret this first vector, 1, 2, as being coordinates on our basis beta. Okay, and again, here's our basis beta, 1 and x. So we're going to take the 1 and the 2 and just use those as coefficients on those vectors in beta one at a time. Okay, so 1 times 1 plus 2 times x. We can do that calculation and notice that you just get 1 plus 2x. Okay, good. And similarly, what comes out on the other side, according to this key fact, should be gamma coordinates. So the 3, 2, we're going to be interpreting those as coordinates on the basis gamma. Gamma looks like this, 1 and 1 plus x. So we're going to put 3 in front of the 1 and 2 in front of the 1 plus x. Okay, and you can do that calculation, just distribute it out, combine like terms, and you're going to get 5 plus 2x. Okay, now, here comes the key step. Okay, they asked us to verify our answer. Okay, what does that mean exactly? Okay, well, the check that we're going to do is, if this key fact is correct, then here's what should happen. If we take 1 plus 2x and substitute it into our transformation t, what should come out is 5 plus 2x. Okay, so 1 plus 2x over here should be our input, and 5 plus 2x over here should be our output. Let's check and see if that's really the case. Okay, so t of 1 plus 2x, by definition, go back to our transformation, it looks like this. We're going to get 1 plus 2x plus 2 times the derivative of 1 plus 2x. Okay, let's see, that's going to be 1 plus 2x plus 2, and then the derivative of 1 plus 2x is just 2. And if you simplify that, 1 plus 2x plus 4, sure enough, you're going to get 5 plus 2x. There's our check. So we started with this vector and substituted into t and got this out. Okay, and so we're good. All right, let's do part B. We should see a similar thing happening there. Okay, so this time our matrix is t going from gamma to beta. Okay, so we need to sneak a peek back a couple of pages. We already calculated this matrix previously to be 1, 3, 0, 1. Okay, they're asking us to take that matrix and multiply it by 1, 2. Okay, if you do that matrix multiplication this time, you're going to get 7, 2. Okay, and again, we're interpreting the first vector as going with this basis. Okay, so 1, 2 we're thinking of as being gamma coordinates. All right, so our basis gamma, let's sneak a peek, that looks like this. All right, so we're going to think of 1 and 2 as being coefficients on those basis vectors. 1 times 1 plus 2 times 1 plus x. Do the arithmetic there, and that's going to give you 3 plus 2x. All right, and then our output basis is beta, so we're thinking of the 7, 2 as being beta coordinates. All right, and our beta basis, that was the standard basis, so we're going to take 7 times the first standard basis vector plus 2 times the second one. That's just going to give us 7 plus 2x. Okay, we're ready to do our check. So if we've done everything right, what that means is that this vector 3 plus 2x should be an input. If we substitute that into our function t, we should get 7 plus 2x out. Let's see if we do. 3 plus 2x. Again, here's our definition of t. So we'll take 3 plus 2x plus 2 times its derivative, and the derivative of 3 plus 2x is 2. You do the simplification there, 3 plus 2x plus 4, and sure enough, you get 7 plus 2x. Okay, so we got the input of 3 plus 2x, the output of 7 plus 2x. That matches these two vectors, and we have confirmed our calculation. All right, let's do one more, just to make sure that you've got the idea of what's going on here. Okay, so this time our matrix is t beta. Okay, I'm paging back and just noting that we calculated this previously to be 1, 2, 0, 1. They're asking us to take that and multiply it by 1, 2, which if we do that, we're going to get 5, 2. Okay, and this time, notice that we've just got one basis, beta, which is serving as our basis for the domain and the codomain. Okay, so we're interpreting both 1, 2, and 5, 2 as going with our basis beta. Okay, let's sneak a peek again. Beta is just the standard basis up here. So we're going to take those and think of those as being coordinates on that. So 1 times 1 plus 2 times x, that's just 1 plus 2x. Okay, and over here in our output, 5 times 1 plus 2 times x is 5 plus 2x. Okay, and our check would be to confirm that if we take the first of those two vectors and substitute it in, we should get the second one out, 5 plus 2x. So let's see. Oh, actually, I think we already did this calculation, didn't we? Okay, if we scroll up, t of 1 plus 2x was 5 plus 2x. That hasn't changed because our formula hasn't changed. Okay, so that's still going to be 5 plus 2x. And again, we started here and we stopped here. We have just confirmed our calculation.